In the next 20 minutes, we'll break down exponential growth, exponential decay, and the core models that appear on real SAT problems. You'll learn how to recognize patterns, interpret equations, and solve questions faster and more confidently. Let's get started. In this lesson, we're going to master the core ideas behind exponential functions, concepts that appear again and again on the SAT math exam. First, we'll break down the structure of an exponential function so you can immediately tell how the initial value and the multiplier influence the graph. You'll learn how to recognize exponential growth and decay, and why the base tells you everything about the long-term behavior of the function. Next, we'll explore how exponential models are used in real SAT problems, whether it's population growth, finance, or bacteria models. We'll also practice converting between different exponential forms, such as turning a growth rate or a percent change into a multiplier. This will help you move between equations quickly and accurately. Then, we'll analyze exponential graphs by looking at intercepts, asymptotes, and how the function behaves as x becomes large or small. Finally, we'll walk through several SAT-style exponential problems step by step, so you'll know exactly how to approach and solve them during the exam. By the end of this lesson, you'll have a solid, practical understanding of exponential functions and the confidence to tackle every related SAT question. On this slide, let's look at the big picture behind exponential functions. An exponential function has the form y equals ab caret x, where a is the initial value, and b is the multiplier that controls growth or decay. If b is greater than 1, the function represents exponential growth. Values increase faster and faster over time, as shown by the blue curve on the right. If b is between 0 and 1, the function represents exponential decay. Values decrease toward 0, just like the orange curve. One of the most important ideas here is that exponential functions change by a multiplier, not by adding or subtracting a fixed amount. That's why the curves bend. They're growing or shrinking by percentages, not by constant steps. Understanding this idea is the foundation for solving all kinds of SAT problems involving population growth, compound interest, bacteria models, and much more. Now, let's take a closer look at how multipliers influence exponential growth and decay. In exponential functions, the key idea is that quantities change by multiplication, not addition. If something grows by r% each step, its multiplier becomes 1 plus r over 100. If it shrinks by r%, the multiplier becomes 1 minus r over 100. For example, a 20% increase corresponds to a multiplier of 1.20, while a 15% decrease corresponds to 0.85. Here's the important part. A multiplier greater than 1 produces growth, and a multiplier between 0 and 1 produces decay. Larger multipliers make the curve bend upward more steeply, while multipliers below 1 make the curve bend downward. In the graph, all curves start at the same initial value. The blue line shows growth with multiplier 1.20. The orange line shows decay with 0.85. And the dashed line represents no change, with a multiplier of exactly 1.00. Understanding how these multipliers work helps you predict how quantities evolve over time and why exponential patterns rise or fall the way they do. Now, let's bring everything together and look at the general form of an exponential function. An exponential function can be written as f, x, equals a times b to the power of x. Here, a represents the initial value, the height where the graph begins. B is the multiplier, which controls how the quantity changes at each step. And x represents the number of steps or time periods. Understanding how each part works helps you see why exponential graphs behave the way they do. If b is greater than 1, the function grows. If b is between 0 and 1, the function decays. In the graphs on the right, the left panel shows how changing a simply shifts the whole curve up or down. The middle panel compares growth and decay by changing b, while keeping the same starting value. And the right panel highlights what x means. Each time x increases by 1, the value of the function is multiplied by b again. This general form gives you a powerful way to model real-world situations, from population growth and interest rates to cooling processes and depreciation. Here are some real-world examples of exponential functions. Exponential patterns appear all around us because many things in life change by a percentage, not by a fixed amount. Let's look at a few important examples. First, population growth. When a population grows by a constant percentage each year, the increase becomes larger and larger over time. Even a small growth rate produces a curve that bends upward, just like the graph on the left. Next, compound interest. This is one of the most important exponential processes in finance. Your money grows by multiplying by the interest rate every year. Because each year's interest is added to the previous balance, the growth becomes faster as time goes on. That's why the curve gets steeper in the middle graph. Another example is radioactive decay. Certain substances decrease by a fixed percentage over time. Instead of dropping to zero immediately, they shrink gradually but continuously. This creates a smooth downward bending curve, like the one shown on the right. A similar exponential pattern also appears in cooling and heating. An object's temperature approaches the surrounding temperature at a percentage-based rate, not at a constant speed. The key idea is this. All of these situations change by a percentage each step, which is exactly why exponential functions describe them so well. Understanding exponential growth and decay helps us interpret a wide range of real-life processes, from biology and physics to finance and everyday phenomena. Here's how you can recognize exponential behavior in real situations. A process is usually exponential when it changes by a constant percentage each time, rather than by adding or subtracting a fixed amount. In exponential patterns, each step multiplies the previous value by the same multiplier, which creates a smooth upward or downward curve instead of a straight line. There are several common clues you can look for. Phrases like, increases by 5% each year, decreases by 12% each hour, doubles every 3 days, or has a half-life of 10 years, all describe exponential growth or decay. On the right side of the slide, you can see 3 examples. A 5% increase corresponds to a multiplier of 1.05, which produces gradual growth. A 12% decrease has a multiplier of 0.88, so the value shrinks a little at each step. And when something doubles every step, the multiplier becomes 2, producing rapid exponential growth. Whenever you see a description that involves percentage change or repeated multiplication, you're looking at exponential behavior. Now that you've seen how exponential behavior appears in real situations, let's look at the 4 main types of exponential problems you'll encounter on the SAT. The first category is growth and decay models. These follow the form y equals a times b to the t. If the multiplier b is greater than 1, the quantity grows. If b is between 0 and 1, it decays. Percent changes are often rewritten as multipliers. For example, an 8% increase corresponds to b equals 1.08. The second category focuses on doubling or halving time. These problems ask how long it takes for a quantity to double or be reduced by half. They use the structure y equals a times 2 to the t divided by k. If something doubles every 3 steps, the multiplier reaches 2 at t equals 3. The third category is multiplier interpretation. Here, you convert between percent rates and multipliers. A 20% increase becomes 1.20, a 12% decrease becomes 0.88, and doubling corresponds to a multiplier of 2.00. The fourth category compares 2 exponential expressions. Even a small difference, such as 1.05 versus 1.03, creates steadily widening gaps over time. These questions ask which expression grows faster and how the difference evolves. Understanding these 4 patterns will help you quickly recognize what a problem is asking and choose the right exponential model to apply. Now let's take a moment to summarize what you've learned so far. Exponential behavior is driven by multipliers rather than fixed amounts. When the base b is greater than 1, the quantity grows, and when b is between 0 and 1, it decays. We also looked at how percent changes can be converted into multipliers. For example, a 5% increase becomes 1.05, and a 12% decrease becomes 0.88. You saw how doubling and halving times describe how quickly a quantity grows or shrinks, and how even small differences in multipliers, like 1.05 versus 1.03, can lead to very different results over time. These ideas are especially important on the SAT. Many questions involve exponential models without directly saying so, and you're often tested on your ability to recognize patterns, convert percentages into multipliers, and compare different models efficiently. By understanding these 4 main types of exponential problems, you now have the tools to approach them with confidence. Next, let's apply what you've learned to real SAT-style practice problems. Here's your beginner-level question. A quantity increases by 8% each year, and your task is to convert that percentage into a multiplier. Remember, a percent increase becomes 1 plus the percent divided by 100. Choose the correct multiplier from the options. You have 60 seconds. Here's the full explanation for the beginner practice problem. The question tells us that a quantity increases by 8% each year. To find the multiplier, we begin by converting that percentage into a decimal. 8% becomes 0.08. This step is important, because exponential growth always works with decimals, not the percent itself. Next, we use the standard growth formula, multiplier equals 1 plus the decimal amount. So we compute 1 plus 0.08, which gives us 1.08. This multiplier tells us how the value changes each year. A multiplier of 1.08 means the quantity becomes 1.08 times the previous year's amount. In other words, it grows a little more than the original value every year. So the correct answer is, multiplier equals 1.08. Here is your intermediate practice problem. A population starts at 500 and grows by 6% each year. Your task is to find the population after 4 years. First, convert 6% to a multiplier. Then apply that multiplier year after year for a total of 4 years. Finally, round your answer if necessary. You have 60 seconds. Pause the video here and try solving it on your own. Let's go through the solution step by step. We begin with the initial population, which is 500 people. Since the population grows by 6% each year, we first convert this percent into a multiplier. 6% is the same as 0.06, so the multiplier becomes 1.06. Next, we apply this multiplier repeatedly for 4 years. After the first year, the population becomes 500 times 1.06, which equals 530. After the second year, 530 grows again by the same rate, giving us 561.8. In the third year, that value increases to about 595.5. And in the fourth year, multiplying again by 1.06 gives approximately 631.24. Finally, we round this result to the nearest whole number. So the predicted population after 4 years is about 631 people. This shows how exponential growth works. Small repeated increases compound over time to create a much larger change. Here is an advanced exponential growth problem. A town's population grows at 4% per year for the first 3 years, then increases to 7% per year for the next 3 years. Your task is to find the population after 6 total years. Remember, you will use 2 different multipliers, one for each phase. You have 120 seconds. Pause the video if needed. Let's carefully walk through this advanced exponential growth problem. The town starts with a population of 2,000 people. For the first 3 years, the population grows by 4% per year. A 4% increase corresponds to a growth multiplier of 1.04. We apply this multiplier 3 times. After year 1, the population is 2,000 times 1.04, which equals 2,080. After year 2, we multiply 2,080 by 1.04 to get 2,163.2. After year 3, we multiply 2,163.2 by 1.04 and get about 2,249.728, which we can think of as roughly 2,250 people. Starting in year 4, the growth rate changes. For the next 3 years, the population now grows by 7% per year, so the new multiplier is 1.07. We take the value after year 3 and apply 1.073 times. After year 4, the population is about 2,407.21. After year 5, it grows to about 2,575.71. After year 6, multiplying once more by 1.07 gives approximately 2,756.01. Finally, we round to the nearest whole number. So the population after 6 years is about 2,756 people. This example shows how changing growth rates and repeated multipliers combine to create significant exponential growth over time. Let's take a moment to wrap up everything we've covered about exponential growth and decay. Exponential change means that a quantity grows or shrinks through repeated multiplication, rather than adding or subtracting a fixed amount. Growth occurs when the multiplier is greater than 1, and decay occurs when the multiplier is less than 1. There are several key clues that tell you a situation is exponential. If you see a % increase or decrease, a doubling time or half-life, or a growth rate given for each time interval, those are strong indicators that the process follows an exponential pattern. These ideas appear all around us, in population changes, financial growth, bacteria and viral spread, radioactive decay, and many other real-world situations. The more you practice, the more natural these patterns will feel, and the quicker you'll recognize how to set up the model and choose the correct multiplier. Thank you for following along. Keep practicing, build your intuition, and you'll become much more confident with exponential models on the SAT and beyond.